good lesson. It's kind of more fun stuff with integrals. In this situation, we're finding an average value of a function. Now, that kind of doesn't make sense. I'd like you to think about it as like the average of an infinite set of values. Of values or of data. You know, and it starts with how we know how to calculate averages. If I ask you to find the average of 3, 5, 7, 9, 15, 18, and 20, what do you do, Mr. Glubke?
Find the mean.
How do you find the mean? How do you find an average, Mr. Owusu?
Add them all and then divide by how many numbers there are.
Good. All right, we got it. So we're going to add all these numbers up. I know. You weren't expecting me to call you out. It's okay. You add all these numbers up, and then you'll divide it by how many numbers you have. 1, 2, 3, 4, 5, 6, 7. Okay. Now I'm not going to divide. I'm just going to multiply by 1/7. That's the same thing. Okay. Well, that's like, and we're going to find the general form of finding an average using, math notation. We're going to call these all A values. This is A1, this is A2, this is A7, okay? And that just shows you it doesn't matter what these values are. If I wanted to find the average, I would take the sum of all of these A's. I'll call them AIs, but I'll designate that we'll start our I's at 1, and we'll go to 7. So it's a 1, 2, 3, 4, 5, 6, 7. And then I'll multiply this by 1/7. Okay, that's how you find the average of this set of data. Well, let's say I had a different amount. Say we had more, say we had less. Say I could add a bunch of numbers and I had 30 as my last value, but I don't know what number that was. We would call that the nth number. It could be the 30th, it could be the 50th number, it could be the 1000th number. We'd call it AN, the last number. And in general, the formula for the average of a set of data would be the sum of a bunch of values, we'll call them A's, from 1 to n, my last one, and then I'll multiply that by 1 over n. Whatever the number is under my last A, that'll tell me how many numbers I have. So like in this situation, this 20 was A to the 7th, so that tells me I have a total of 7 numbers. That's why I multiplied by 1/7. Whatever this n is for this last value, I would say multiply by 1 over that n. Okay? Just helps things make sense by saying it's the first, second, third, fourth, nth number. Well, let's switch from the finite world to an infinite world, where you have an infinite set of values. Now, where do we see an infinite set of values? Graphs, functions, have infinite sets of values. This could be like a function between two certain x values. And it doesn't matter what the x values are. I could just pick 2 random x values. But let's say this is our function between 0 and 4. Okay? So I could kind of graph this set of values. It's an infinite set of values. We have an infinite amount between these two. We have an infinite amount between these two, infinite. So it covers all the decimals and all the decimals between the decimals. And in between even 2 decimals really close together, there's still an infinite amount of values. And we can kind of show it here. So we got 0, 1, and then we got 1, 2, 3, 4, 7. Okay? And I don't know how these, points are plotted. They could be all over the place, but if I just connect these 2 points with a line, this line represents an infinite set of data, an infinite amount of values. Okay? Well, the question we're trying to answer is, what is the average of that infinite amount of values? Okay? That's what we're trying to find. Well, now it's a little tough, right? The averages we've been finding in our lives have been finite. We've been able to add up all of our numbers and divide by the amount. Well, in this situation, it is impossible to add up all of these numbers, and to divide by the amount would be like to be dividing by infinity. That kind of is like not able to be thought of properly, and it's not able to be done. Okay? But maybe we could think about what our average would be. Like, what if I connected these 2 points with a straight line, and this is an infinite set of data? Where do you think the average would be for this infinite set of values? Yeah, right smack dab in the middle at 4. And this should make sense because we have, the same amount of values above this line, and we have the same amount of values below the line. Okay? So that's cool. At least we can kind of picture what the average would be of an infinite set. We can picture that being an actual value. It's not like the value doesn't exist. And I can kind of connect things differently. Maybe I connect this 0.01 and 47 like this. Well, can you picture where the average value would be now? Where would it be in relation to our original one? Yeah, it'd probably be higher, right? Because it looks like we have more values up here than down here. So my average is probably going to be, maybe up here. So we can kind of see how it's going to exist. Just got to figure out where it is. And we can see how the average isn't always going to necessarily be smack dab between our first point and our last point. And then, of course, I could show you just if we were like concave up, how the average would be probably underneath that midpoint. And you can't say that. We don't know. If maybe it was concave up in a specific way, it would be like half the way between 4 and 1. But it could be anything. It could be like this. And then it's like, well, I don't know if it's half or a quarter. I kind of can see that it's going to be underneath 4, right? But exactly where, now it's tough. So what we're going to do is we're going to try to discover maybe a formula that will help us figure this out. Okay? So I'm just going to find where the displacement is 0. Well, no, the displacement here is all positive, right? Because it's all positive areas. Yeah, that's probably right. We might want to find comparison to the line where the area would be 0. That might be correct. I'm not sure. But let's figure it out. Let's figure it out. There's another way. Okay? So let's talk about our general form for an average. It is the sum of a bunch of numbers times the amount of numbers, right? We're starting at our first number, we're going to the nth number. Whatever the nth number is tells me how many numbers I have, okay? Well, this is the finite world. What would change this to be an infinite world? n would be infinity, right? Now, we're not going to just plug in infinity here because, like, 1 over infinity we think is 0, and it is. So we don't want to think about it that. Instead, we'll say let's approach infinity. Let's talk about n approaching infinity. So instead, I'll put a limit right in front here. Okay? So this is a general average formula for an infinite set of data. Now, this should look familiar to you. An infinite sum. Okay? When did we use an infinite sum? Areas under curves. Integral is actually the first time I introduced to you the integral symbol. It was to replace this. Okay? And let's remember how we first talked about an area under a curve. We took the limit as n approaches infinity of a sum of a bunch of function values, which were heights, times a bunch of widths, which were kind of subintervaled, and to find the width of each subinterval, we took our kind of endpoint minus our beginning point, we divided by the amount of subintervals n, right? Well, these two things are really close to being the same. Being the same. But they're not exactly the same, okay? We use the notation for this. We said eliminate this, use b to a here to denote the bounds, and then f of x, and as n approaches infinity, this became dx. Okay, so the a and the b went here. As n approached infinity, this became dx. Well, I can't just say this is going to be the area from a to b of f of x dx up here, because I don't have an a or a b. I just have values times 1 over the amount of values. I don't know where to start, I don't know where to finish, so I can't just say it's the same. I need to add something so that these are the same. So let's look at the differences. The first difference I notice is that I got an f of x and I got a bunch of a's. Well, we just talked about how an infinite set of values can be just function values. So I can just easily replace that, no big deal. What's the other thing I'm missing?
A and B.
Yeah, I'm missing this b minus a, okay? So I need a b minus a up here for this to be the same. Now, I can't just add it. That would be against the rules of algebra. I can kind of manipulate this by multiplying by a version of 1. If I multiply the top and bottom by b minus a, that's not changing this formula for the average of an infinite set of values. It's just making it look different. Well, now I can move this b minus a up above the n, and all of a sudden, this turns into that. Well, now that this is the same as this, I can go ahead and take this and replace it for this guy. And now I have a formula that might make sense to me for the average of an infinite set of data. Turns out, if you want to find the average of an infinite set of data, you find the area under the curve that the data kind of produces. You know, if you graph out all of the data, you find the area under that set of data, and then you multiply that area by 1 over b minus a, and poof, you get the average. So typically when you look at this, the 1 over b minus a will come out in front of the integral, just so you're not confused. And you can say the average is 1 over b minus a times the area from a to b of your function. Well, you can use the fundamental theorem of calculus if the infinite set of data was a function. If it's just almost like random points, completely random, and we can't find the antiderivative, then we wouldn't have to worry about that. But we're going to say, hey, this infinite set of data can be expressed as a function. So I can find the antiderivative of that function, which means I can find the area. Or I could use my calculator. Yeah, I'd probably give you the function. Okay? So we state that the average value of an infinite set of data which can be expressed as a function is just the area under the function times 1 over b minus a. Important things to note. If you want to find the average of something, you would find the area of that something and multiply it by 1 over b minus a. If you wanted to find the average velocity, you wouldn't find the area under acceleration or the area under position. You would make sure you'd take 1 over b minus a, and then in here was your velocity. Not the absolute value of velocity, just velocity. If you had a population function, P of t, and you want to find the average population over a period of time, well, make sure you put P of t in here. This is where things start to get confusing, because if you didn't have a calculator and you had to find the area under this, well, you use the antiderivative to find the area. That doesn't mean you're finding the average of the antiderivative. You're still finding the average of the population. You're just using the antiderivative to find that area. It's going to get confusing, but it's not that bad. It really isn't. Okay? So whatever you want to find the average of, take and find the area under that average. So after this lesson, we have a bunch of stuff, a bunch of information that is and can be obtained by using integrals. I'll even add a fifth one. So the first guy, when we first introduced this, we said, okay, integral infinite sum, it's just an area under a curve, or an area between a curve and the x-axis from A to B. Well, then we found out how you can find the area under a curve by understanding the fundamental theorem of calculus, and that areas are just equal to change in antiderivatives. So if I talk about this, and we could use this as well to find future values that we don't know, just given an unknown and given the derivative, we can say that, yes, this is the area under f prime, but this is also the change in its antiderivative f. from A to B, which of course is f of b minus f of a using the fundamental theorem of calculus. Now this is awesome. So this right here no longer just means area. It also means a change, an overall change. Not a change in a rate, but an overall change. Now, if we put just velocity instead of f, we talked about straight line motion. If I find the area under velocity, that is my change in x, which is my displacement. If I take any negative velocity and make it positive, if I have positive velocities and I keep them positive and I find the area under that, turns out we take all of our negative displacements, make them positive, add all of our positive displacements together, and we would have distance. And finally, if we want to find an average value of a function, we can just take the area under the function, multiply it by 1 over b minus a, and there's our average f of x between A and B. All right, now I'm going to start doing an example problem. There's going to be more example problems on the video, but right now I'm going to pause and give you your homework, and you can watch those example problems at home. All right, let's do this one. Find the average value of this function on the interval from 1 to 4. Check to see that the area under f of x equals the area under the average. You actually don't have to worry about that. That was just a corollary that is not important. But the question that I want you to find the answer to is definitely this one. For what x does the function equal the average? A way you can do that, or it can be asked of you, would be to find c such that f of that c value equals the average of the function like that. Okay, so we'll do that. So first let's find the average of this function on the interval from 1 to 4. Now before I even find the average, I'm going to just think about this and make sure I understand where the average is probably going to be. So I'll start with sketching my function. And you don't have to do this. You know, you can just blindly go ahead and start plugging in values and find, using your formula, find what the average value is. But it's also helpful to kind of see whether or not your answer is going to be right. So I got this point 1, 1, and I'll have the points, sorry, we're going to go from 1, 1, not from 0, 1. So 1, 1, and then 2, 3, 4. If I plug in 4, 4 squared is 16, times 3 is 48, minus 2 times 4, that's 40. Okay, so up here at 40. And we know since it's 3x squared minus 2x, it's going to be like a parabola opening upward. So if this is 1, this is 40, right smack dab in between would be like 20 and a half. I could probably tell that my actual average is going to be underneath this. It looks like since we're concave up, we are going to be having more function values like below this midpoint than above it. So that's going to help. So I can tell that whatever answer I get, better be probably less than 20. So let's figure out the average. The average of f of x is just going to be equal to 1 over b minus a times the area from 1 to 4 under 3x squared minus 2x. Now, of course, if I had my calculator, I could calculate this, but just so you can remember how to calculate this without a calculator, let's find the change in the antiderivative. So I have 1/3 times, this would be the change in x cubed minus x squared from 1 to 4, which would be 1/3 times 4 cubed, 16 times 4, 64. minus 4 squared minus 0, because it'd be 1 cubed minus 1 squared. So I get 64 minus 16, so that's 44, not thinking, 48, yep, there you go. So I'd have 1/3 times 48, which would be 16. All right, that's it. So that looks good to me. If the middle was at 20.5, I thought my average had to be a little bit under there. Boom, it is. Great. So that was part 1, to find the average value. Now part 2 is going to be to find the C value such that f of C is equal to the average. So for what x does the function equal the average value? Well, this is a function value. This is the average. Here's 16. I'm trying to find the x, where f of x is equal to 16. You know, maybe it's like right here between 2 and 3. I don't know. This is a bad sketch. Okay? So I need to find that function value. How do I do that? Well, you set your function equal to that average value, and then we solve for x. Now, in this case, I know that I can't really solve this by hand really well unless I could factor, and I think you can factor this. But let's say I don't want to bother. Let's say I have my calculator handy. Let's figure out just the solutions quickly. Well, in my y equals, I would just graph the 3x squared, 3x squared minus 2x, and I'd graph y equals 16, and I'd see where they intersect. Probably change my window to be from between 1 and 4, that's good, and probably my y's need to go up to like 20 so I can see it. I screwed that up. Window from 0 to 5, from 1, why don't we go to 1 to 20. There it is. I think it might be between 2 and 3. Second, calculate the intersect. Enter, enter, enter. We're pretty close. 2 and 2/3. There you go. Between 2 and 3. Shocking. Okay, so x is equal to 2 and 2/3. That's 8/3. That is the C value that we were looking for, such that the function is equal to your average. So for this x value right here, 2 and 2/3, we produce that y value of 16. Okay? Good. Let's do another one. Given the velocity is 6t squared minus 3t, find the average velocity from 0 to 4. When does the velocity equal the average velocity? Or when does? Well, simple. The average is just 1 over b minus a times the area from a to b of whatever I'm trying to find the average of. If I'm trying to find the average velocity, I best be having velocity in my integral. Okay, and now I'm just going to use my calculator to calculate this. I have 1/4, 0.25 times math 9, the integral of 6t squared minus 3t with respect to t from 0 to 4. I say t, but I mean x. 26, voila. That should make sense. I always like to check. Now I have the 0.00. I'll have the 0.4 if I plug 4 into 6t squared. 6 times 4 squared minus 3 times 4. I get 84. Okay, now 6t squared minus 3t is going to look like that. So the middle of 0 and 84 is 42. I know that the average is definitely going to be underneath that since we're concave up. So 26 sounds pretty reasonable. It's almost like a little bit lower than I thought it would be. I guess it's because we are, maybe opening up a little bit more like that. Maybe that's more like it. Okay, now finally, when does the velocity equal the average? So for what time does this equal that? Use your calculator. Let's figure that out. 6x squared minus 3x over equals 26. Let's set the y max to be like 30 so I can see it. Sometimes if you can't see it, the calculator doesn't find it. See, there you go. There's that concave upness. Second calc intersect, enter, enter, enter. 2.34. 66. Round to 3 decimal places. 2.347. Okay, that was perfect. Next question. Given the velocity is 3t squared, find the average position of the particle from 0 to 2. Given the particle's initial position is 3. For what time t does the position equal the average value? Okay, average position is what I'm trying to find. It's very important for you to be slow, be careful, read your questions. This is average position. I need to find average position. I'm given velocity. If I plugged in 1/2 times 0 to 2 of 3t squared, this would be the average velocity. So don't make that mistake and just blindly plug in whatever you see. Think, read, answer. So I need to find average position. I best be having position in this integral. How do you find the position given the velocity? Well, you're going to have to find the antiderivative. So position is going to have to be t cubed plus a c. We're told that the initial position is 3. So when t is 0, that's going to have to be 3. 4 times t does the position equal the average value? Okay, that'll be part 2. So right now I just need to find this. Now, this is the average position. If I wanted to calculate this without a calculator, I could. It would just be the change in the antiderivative, 1/4 t to the 4th plus 3t from 0 to 2. That's not meaning I'm finding the, average of this antiderivative. I'm still finding the average of my position. Okay, so 2, 4, 8, 16 divided by 4. So this is 1/2 times 2, 4, 8, 16 divided by 4 is 4 plus 6 minus 0. That's 5. Okay, and that can be checked if I wanted to. 0.5 math 9 t cubed plus 3 with respect to t or x from 0 to 2. Boom, 5. Okay, and then for what time t does the position equal the average value? That's the whole find c such that f of c is equal to f of your average. Well, when does t cubed plus 3 equal 5? I can actually calculate this by hand. That's when t cubed is equal to 2, or t equals the cubed root of 2. Okay? Sweet. Next one. I could have a crazy function. Here, the rate at which water is entering a tank is given by R of t. This is the rate at which water is entering a tank. R and t is gallons per minute, t is minutes. What is the average rate of water flow between 2 minutes and 5 minutes? And we'll go ahead and not worry about the second piece for now. Okay, well, if this is the rate at which water is entering a tank, the average rate would just be 1 over b minus a, so that's 1/3, and then the area from 2 to 5 under 4 root 1 plus t squared dt. Okay, you can calculate that. If this was the amount at which water is in a tank, they asked you for the average rate. All of a sudden, if this was an amount and this was find the average rate that water is flowing, you would have to take the derivative of the amount equation to find the rate at which water is entering the tank, and then put the rate in here. See how that could be tricky. Next question, approximate the average temperature using a trapezoidal Riemann sum. So here's that set of data that we've seen so often. We want to find the average temperature, probably over the 20 minutes. Well, to find the average temperature, it would just be 1 over b minus a, so 1 over 20 times the area from 0 to 20 under the water temperature, W of t. Well, I can't find this because I don't know the function, but it just told me to use a trapezoidal Riemann sum to get that average. So let's do that. Unfortunately, these intervals are not the same, so I can't use my shortcut of the 1/2 first plus last, 1/2 your width, then first plus last plus double your middle. So instead, I got to go all one at a time on this. So 1/2, 4, 55 plus 57.1. The next one, 1/2 between 4 and 9, the width is 5, 57.1 plus 61.8. Okay, and you would keep going. Let's just do that in the calculator. Try to go as quick as possible. So 1/20 times the quantity, 0.5 times 4 times 55 plus 57.1. Close. Plus 0.5 times 5 times. Delete that. B7. .1 plus 61.8 plus 0.5 times between 9 and 15, that's 6. 61.8 plus 67.9 plus 0.5 times between 15 and 20, it's 5. 67.9 plus 71. This is a cruel problem that I gave myself. We should close the parentheses one more time. Everything should line up. 62.89. Now, I feel really good about this answer because it's between 55 and 71. So I feel fairly confident. Now, my question is, would this be the same as if I found just the average of these 4 values? No, it wouldn't be. So that's good. It's because the areas are going to be different. So since these intervals are different, this is going to be different than just this normal way of calculating this average. If I take this and divide it by 5, I'm not going to get 62.89. Aha! Okay? Shows you that considering this time and the average being the area under all of these degrees, this would give you the right answer, the more accurate answer. Okay? At least if things go the way they're supposed to and don't go crazy between 55 and 57. You know, it just kind of goes straight up to 57, then to 61, to 69. Cool. All right, that's it. Average. Same as areas under curves. Derived by using the general average formula and then comparing that when we took the limit as n approaches infinity to being very similar to the area under a curve, Boom, we connected it. Boom, we got the same. Okay, fun stuff. Got goes.